Namaste. This is Nataraja Pillai again. Welcome to the class on thin shock layer today. Right? In the last classes, we had a discussion on what is hypersonic flow and had a overview of how the subsonic airplane looks like, how a supersonic airplane looks like, and then what may be the characteristics of the hypersonic vehicle. And then we had a discussion on classification of hypersonic vehicles, whether it may be a re-entry or a launch or whatever it is, right? And we came to a conclusion with the definition, right? Like by rule of thumb, we can say the hypersonic flow is more than Mach number 5, and so on. And we found that there are some characteristics or phenomenon associated with the hypersonic flow. Now, today we will discuss one such phenomenon called thin shock layer. I will give an introduction and then I will proceed with the thin shock layer. So, as usual, I acknowledge the content from John D. Anderson Jr., hypersonic and high temperature gas dynamics. Right. So, we know the characteristics. As of now, we know. You can, I used to say in the class, believe me, right? Believe me for certain things. Say, if the characteristics in a flow have a thin shock layer, entropy layer, viscous interaction, high temperature flows, low density flows, if any of these are associated in a flow, then we can say that the flow is hypersonic flow. Uh, whether it is a Mach number 3 or Mach number 2 or Mach number 4 or Mach number 7 or Mach number 20, right? Okay, so these are the characteristics of phenomenon we know, right? Thin shock layer, entropy layer, viscous interaction, then high temperature flows and low density flows. Today we will look into thin shock layer. Every class we will have a deep discussion on one by one. So today's title or topic is thin shock layer, right? Let's go to the topic. So this is again a problem, right? We know from the PL row that whether it is 3 or 12, right? Anything can be a hypersonic flow. So with this definition, I will move, right? So by rule of thumb, we have the Mach numbers classified for the different flow regime. So less than 3 we consider as an incompressible flow, and Mach number less than 1 is subsonic flow. Then zero point 0.8 to 1.2 we consider as a transonic flow, and Mach number more than 1 is considered as a supersonic flow. Now, more than Mach number 5 or above, we consider by rule of thumb is hypersonic flow. Right? So, it is like a greater than 5 is hypersonic. Now, there is a question. Why, sir? Why it is more than 5 can be considered as a hypersonic flow? Whether there is something happening in between 4.99 and 5.01, like we say in the supersonic flow, when the velocity reaches Mach number 1, there is a formation of shock wave and the drag increases enormously. In fact, it doesn't happen exactly at Mach number 1, but it starts before that Mach number, where we consider at Mach number 0.6, 0.7, whatever it is in the free stream. But some point in the flow where the Mach number is equal to 1 because of the acceleration of the flow, then we call that as a critical Mach number, right? So, is there is something happening in the hypersonic flow where the 4.99, the Mach number reaches 4.99, and immediately at the Mach number 5, there is something happening? Uh, Nothing happens, in my opinion. But that is why we say whether something turns from green to red or there is a clash of thunder, right? But only thing we name something called, there is a surface We have according to the oblique shock theory, we consider there is a deflection, flow deflection angle, right? Wedge angle and the flow deflection. Right? So the distance between the body and the shock, we call that layer is a shock layer. But simply by calling that as a shock layer at Mach number 5 does not make any big difference. We call it as a shock layer. That's all. Right? So now we are very much clear that at the Mach number 4.99 to 5.01 there is nothing happens. Right? So rather hypersonic flow is best defined as that the regime where certain physical flow phenomena becomes progressively more important as the Mach number is increased to higher values. So in some cases, one or more of these phenomena might become important above Mach number 3, whereas in some other case it may not be compelling until Mach number 7 or 8. Right? So it depends upon the geometry, it depends upon the flow, it depends upon the existence of the phenomena, that is the hypersonic flow. So hereafter, by a rule of thumb, if somebody asks what is hypersonic flow, we can say that more than Mach number 5 can be considered as a hypersonic flow, but by definition, our definition is very clear that these phenomena, if it occurs, these phenomena becomes progressively more important, then that particular Mach number is called hypersonic Mach number. Right? Maybe in certain cases the Mach number 3 may be a hypersonic flow, in certain cases Mach number 7 may not be a hypersonic. Right? Okay, let us recall the oblique shock theory we have studied in compressible flow, probably modern compressible flow by John D. Anderson or gas dynamics by E. Radhakrishnan. Right? You have studied that in the fifth semester or so. Um, we know that there is a increase in density across the shock wave, right? When there is an increase in Mach number. So we say that at a higher density, the mass flow behind the shock can more easily skew through the small areas. And for a flow over a hypersonic, this means that the distance between the body and the shock can become small. So this is a typical oblique shock theory where there is a formation of oblique shock wave, and this is a free stream velocity or flow upstream of the shock, right? And this is downstream of the shock, and we can say that here the beta is a shock angle, and we can consider this as a theta is a off wedge angle, right? So there is a formation of shock wave, and this oblique shock, the characteristics before the shock wave is P1, T1, rho 1, and M1, and after the shock, we consider that as P2, which is greater than P1, and T2, which is greater than T1, and the rho 2, that is the density, which is greater than rho 1, and the Mach number M2 is greater than M1. And theta is a wedge angle, and beta is a shock angle. Now, the flow field between the shock wave and the body is defined as the shock layer. That is very clear now, right? Say in the case of the shock wave and the body, and this area is a shock layer, right? So let us say at Mach number 1.2, that is obviously a supersonic flow, where you have a shock wave, oblique shock wave, and this is a wedge angle, and you can see the shock layer is quite thick shock layer, right? Now assume that Mach number is more than 5, right? When the Mach number is more than 5, there is a shock, and this is a wedge, and you can see the layer, the shock layer, right? The oblique shock occurs very much close to the body, and the shock wave and the body, the layer is called shock layer. So from supersonic to hypersonic, we can say that the shock layer is becoming very thin, right? The shock layer become very thin. When the shock layer becomes thin, what are all the problems occurs that we will see later. But first point we need to know, from supersonic to hypersonic Mach number or increasing in Mach number, there is a decrease in the shock angle, and the decrease in shock angle, then the distance between the shock angle and the body is keep on decreasing, and that particular area is called shock layer, right? So assume at the Mach number 36, the flow is calorifically perfect gas with the gamma is equal to Cp by Cv is 1.4 over a wedge of 15-degree off angle, right? And from the standard oblique shock theory, we can understand that the beta, that is the shock angle, is 18 degrees, right? So we can see the shock layer that is becoming very thin. Hope you can understand what is shock layer, right? What is shock layer and what is thin shock layer? Thin shock layer happens only at the Mach number higher, right? Higher Mach. So the region between the shock and the body is named as shock layer, and we can go to the discussion on theta beta m relation, right? We have already studied theta beta m relation. Now assume that theta is a wedge angle, and considering the constant theta, right? In the case of we consider the wedge of theta, right, and the constant wedge angle. Only we vary the Mach number, the free stream Mach number we vary. So let us vary the Mach number and see. This usually a exercise in the class where for a constant theta, change in m, that is the free stream Mach number, and calculate beta. Okay. Calculate beta. So when you calculate beta, uh, the shock angle keeps on decreasing with increase in Mach number, right? So the shock layer becomes so thin. As of now, I consider only the shock wave, right? Shock wave under the wedge angle. So I consider the shock layer is so thin, right? But again, another problem comes if the high temperature chemically reacting effects are included, then the shock angle will be much more smaller, right? Because at very high speed, you know that very high velocity or Mach number, the temperature on the surface will become very high, and then the flow will be chemically reacting. That we will see in detail in the next classes, right? So the point here is because of the theta beta m relation, the increase in Mach number leads to decrease in shock angle, and hence the shock layer become very thin, and adding the effect of high temperature chemically reacting effects, the shock layer become much more thin, right? So it is a basic characteristic of a hypersonic flow that the shock waves lie close to the body and the shock layer is so thin. Hence we name this as a thin shock layer, right? And in turn, other effects like uh, this creates some physical complications such as merging of shock wave itself with a thick viscous boundary layer on the surface, right? We know that at the body surface there is a viscous layer, right? So the viscous layer and the shock wave interacts with each other, right? The problem becomes very important in low Reynolds number also, but at a high Reynolds number, that becomes a very important criteria. See, there is two phenomena. One is the formation of boundary layer on the surface, but your shock wave, right? The shock wave is really moving towards the surface. Then that particular discussion of shock wave and how it interacts with the viscous boundary layer, that became a topic, right? Anyway, we use this particular concept and we study in detail the thin shock layer, right, in the later cases. But here you need to understand only one point, right? Say the shock wave coming close to the body, and we have a chemically reacting flow at a very high temperature, and there is a problem of the viscous layer boundary. The viscous boundary layer also can interact with the shock layer. Now, we use this approach of thin shock layer to calculate, usually, in the basically Newtonian theory, modified Newtonian theory, right? Newtonian theory by considering the centrifugal effect, and all these things we will study a little later in the same hypersonic course. So by this way we can calculate, we can do some calculation to calculate the coefficient of pressure and all those things. This is a kind of approximate calculation in hypersonic aerodynamics, right? So we will study Newtonian theory, modified Newtonian theory which consider the centrifugal effect and all those things little later, right? So thin shock layer case, we have a shock wave angle on the y-axis and the deflection angle on the x-axis for a oblique shock relation. See, by considering Mach number 2, 2.5, 3, 4, 5, and 8, by having a constant angle, you can see the constant angle of deflection angle of 15 degree. You see the corresponding shock wave angle. So, say Mach number 2, then the Mach number is 2, right? You see, we will consider a particular case of Mach number 2 where the deflection angle is 15 degree and the shock wave angle is 43 degree, and we are increasing the Mach number to Mach number 2.5, then it becomes around 38 or so, and increasing the Mach number to 3, then it becomes 33, then Mach number equal to 4. When the Mach number becomes 4, the shock wave angle becomes around 26 or 27. Like that, the shock wave angle is keep on decreasing. Right? So when the shock angle is keep on decreasing, we know the shock layer, by definition, the shock layer is the region between the shock angle and shock wave and the deflection angle, right? Wedge deflection angle. So that is keep on decreasing and it becomes thin shock layer. So the summary, I can say that hence the thickness of the shock layer decreases with the increase in Mach number for the same flow deflection angle theta. Therefore, the hypersonic flows have thin shock layer. Right? So this interpretation of shock layer thinness for calorifically perfect gas is also applicable to thermally perfect gas and chemically reacting flow, right? So the complexity of the flow field increases due to the thin shock layer when the boundary layer thickness and the shock layer thickness become comparable, right? So we understand the effect of the thin shock layer here, right? This is the first phenomena we need to understand. So I stop at this point on this topic, thin shock layer. We will study thin shock layer theory little later, but this is to introduce you the thin shock layer in hypersonic, right? Thank you very much.